Alright. Let's go into a more straightforward determination of KEQ. Just run the reaction, experimentally determine the concentration of reactants and products in the equilibrium mixture, and then you plug it into your expression for KEQ. So let's look at this simple example. Let's say you've tried to prepare a 0.1 molar solution of some acid HZ. That's a fictitious formula right there, hypothetical. So let's say you tried to make a 0.100 moles per liter solution, and you found your hydronium ion to be 0.001 at equilibrium. What's your Ka of Hz? If I'm interested in the Ka of Hz, what's the reaction I'm interested in? Hz gives me what? What's the product? H3O plus or H plus plus Z minus, right? And so what you need to do is set up an ice table here. What's the initial concentration of Hz that we have? 0.100. You know this is a this is an acid, so it's going to ionize, right? So you're going to lose, let's start off with none of the H plus and none of the Z minus. So you're going to lose X moles per liter of Hz. How much H plus are you going to make? X, right? For every mole of Hz you lose, you gain a mole of H plus and a mole of Z. So what would be your equilibrium concentrations? This is going to be 0.100 minus X. That's going to be X, and that's going to be X. So what's my Ka? What's the expression for Ka? Ka is H plus times Z minus over Hz, right? And so what would it be? It's going to be X squared, X times X over 0.100 minus X. Do I know what X is? According to this, when you did the experiment, you found the hydronium or the H plus concentration, this H plus concentration, to be X. To be 0.001, and that is X, right? You found it to be 0.001. So X must be 0.001. That's what's given. So if I know what my X is, what can I do now? I can solve for Ka. How do I solve for Ka? 0.001 times 0.001 over 0.100 minus 0.001. And that gives me 0.000001 over 0.099, right? That gives me how much? 0.001 times 0.001 divided by 0.099. This is 1.01 times 10 to the negative 5th. How many sig figs should I have here? Didn't give you much. I have one sig fig here, so it's just 1 times 10 to the negative 5th. Okay? That's your Ka. So you can just use your stoichiometry. You set up an ice table, figure out the final concentration. If you know one of these final concentrations, you can figure out the others. So what's the final concentration of H plus? It's X, right? Z minus is X. Hz is 0.1 minus X. Let's say you tried to make a 0.2 molar solution of base B in aqueous solution, and you found the hydroxide to be 0.004 at equilibrium. What's the Kb of B? Okay, what reaction are we looking at here? Kb means what? B is behaving like a base, proton donor or acceptor? A base is a acceptor. So base plus water, it will accept a proton, gives you BH plus, and your other product is hydroxide, right? So you set up your ice table again. Initially, you have 0.2 moles per liter of base. Water, you don't worry about. You have large excess of that. That's your solvent. Activity of that is 1. You have none of this and none of that. Okay. And then what would be your changes? You lose X moles of this. You make X moles of that. You make X moles of that. And what would you have at equilibrium? 0.200 minus X. And this is going to be X. And that's going to be X. What's your expression for Kb? Products of a reactants, right? So concentration of BH plus concentration of hydroxide over concentration of B. Activity of water is 1. So BH plus is X, hydroxide is X, and B is 0.2 minus X. So this is going to be X times X over 0.200 minus X. And I'm just have to plug it in. What is X? It says here hydroxide was found to be 0.004 at equilibrium. So this is 0.004. So you just plug in X equals 0.004. That gives you how much? 0.004 squared over 0.196. 0.004 minus 0.004 divided by 0.196. That's 8.2 times 10 to the negative fifth. Since I only have one sig fig here, it's 8 times 10 to the negative fifth. Okay? Okay, comment. You may be wondering, why did I say H plus was 0 to begin with? Doesn't water have H plus, like 10 to the negative 7? Right? So I'm making an assumption there that there's hardly, that 10 to the negative 7 is negligible. In fact, what do you see? How does 10 to the negative 7, which is 0.000001, compare to 0.001? It is negligible, right? So you can ignore it. Now sometimes you might not be able to ignore it, so you have to be alert to that possibility. But most of the time, this level, we don't ask you questions like that. But one thing you'll realize, though, is that this one, the fact that this Hz produces 0.001, that diminishes the H plus from water itself. Because how much H plus can water give you now? Okay, remember your H2O outer ionization gives you H plus plus hydroxide. Okay, your H plus is now at least 0.001, right? So if this water is going to give you more H plus and hydroxide, okay, it's not going to give you 10 to the negative 7 anymore. Basically, what did you do by adding that 0.001? The Chatelier's principle says you've shifted your reaction to the left. So this X is going to be significantly less than, even less than 10 to the negative 7. What's that X going to be? Well, you can find out what that is. You can say, well, 0.001 plus X, that's my H plus, right? This is my H plus. And my hydroxide is X. That would be 1.00 times 10 to the negative 14. And you see that if you solve for X there, you'll find that X is even lower than 10 to the negative 7. So once you put acids and bases in water that significantly increases the H plus or the hydroxide, you can pretty much ignore the contribution of the autoionization to the H plus and hydroxide. Basically what an acid and a base does, okay, if you add acid, you're suppressing your reaction. Okay, so Le Chatelier's principle, you're shifting your autoionization to the left. If you add more base, you're adding more product, you're shifting your autoionization to the left. So you can pretty much ignore. If you're getting concentration of H plus and hydroxide that's greater than 10 to the negative 6, you can pretty much ignore the contribution from the autoionization of water. Okay?